The minimum depth for a counter-poise grounding system at the four corners of a metal building depends on several factors. These include soil resistivity, the season, whether it is dry or wet, the size of the building, and the grounding requirements of the equipment being grounded. Here's a general guideline based on typical soil conditions. The typical minimum depth for the counterpoise itself is 24 inches. The grounding electrode conductor, often abbreviated as GEC, connecting the counterpoise to the building steel should be buried at least 18 inches below the surface, according to National Electrical Code Section 250.107. Therefore, the total minimum depth is calculated as 24 inches for the counterpoise plus 18 inches for the grounding electrode conductor, which equals 42 inches. In areas with low soil resistivity, such as clay soils, the minimum depth can potentially be reduced. Conversely, in areas with high soil resistivity, such as sandy soils, the minimum depth may need to be increased. If possible, install the counterpoise during the wet season, as the soil is generally more conductive at that time. It is also advisable to compact the soil around the counterpoise to improve contact between the counterpoise and the earth. The size of the building generally does not directly affect the minimum depth required, but it may influence the length and number of conductors used in the counterpoise system. For any specific application, it is always recommended to consult with a qualified electrician or a grounding engineer to determine the most appropriate minimum depth for the counterpoise grounding system. Soil resistivity is a critical factor in determining the effectiveness of a grounding system. Low soil resistivity allows electrical current to flow more easily into the earth, providing a better path for fault currents and reducing the potential for electrical shock. High soil resistivity, on the other hand, makes it more difficult for current to flow into the earth, which can compromise the effectiveness of the grounding system. Soil resistivity is typically measured in ohm meters or ohm centimeters. Several factors can affect soil resistivity, including the type of soil, the moisture content, the temperature, and the presence of dissolved salts. Clay soils generally have lower resistivity than sandy soils due to their higher moisture content and finer particle size. Moisture content is one of the most significant factors affecting soil resistivity. As the moisture content increases, the resistivity decreases. This is because water is a good conductor of electricity, and it helps to facilitate the flow of current through the soil. Temperature also affects soil resistivity. As the temperature increases, the resistivity generally decreases. This is because the increased temperature increases the mobility of ions in the soil, which facilitates the flow of current. Dissolved salts can also affect soil resistivity. The presence of dissolved salts increases the conductivity of the soil, which reduces the resistivity. In areas with high soil resistivity, it may be necessary to take steps to reduce the resistivity in order to ensure the effectiveness of the grounding system. This can be done by adding soil amendments, such as bentonite clay or groundwater, to the soil. It may also be necessary to install a larger or more extensive grounding system in order to provide a sufficient path for fault currents. National Electrical Code Section 250 covers grounding and bonding requirements for electrical systems. Section 250.107 specifically addresses the grounding of metal building frames. This section requires that metal building frames be grounded to a grounding electrode system. The grounding electrode system must consist of one or more of the following electrodes: a metal underground water pipe, a concrete encased electrode, a ground ring, or rod and pipe electrodes. The grounding electrode conductor must be sized in accordance with National Electrical Code Table 250.66. The grounding electrode conductor must be connected to the metal building frame in a manner that provides a permanent and effective ground path. The grounding electrode conductor must be protected from physical damage. Counterpoise grounding systems are often used in metal buildings to supplement the grounding electrode system. A counterpoise is a network of interconnected conductors that are buried in the earth around the perimeter of the building. The counterpoise helps to reduce the impedance of the grounding system, which improves its ability to conduct fault currents. The length and spacing of the counterpoise conductors are determined by the size and shape of the building, as well as the soil resistivity. The counter-poise conductors must be sized in accordance with National Electrical Code Table 250.66. The counter-poise conductors must be buried at a depth of at least 18 inches. The counter-poise conductors must be connected to the metal building frame at multiple points. The grounding system should be inspected and tested regularly to ensure that it is functioning properly. Ground resistance testing is a common method for evaluating the effectiveness of a grounding system. Ground resistance testing involves injecting a current into the earth and measuring the voltage drop. The resistance is then calculated using Ohm's law. A low ground resistance indicates that the grounding system is effective, while a high ground resistance indicates that the grounding system may need to be improved. Ground resistance testing should be performed by a qualified electrician or grounding engineer. The results of the ground resistance testing should be documented and kept on file. Grounding is an essential part of any electrical system. A properly designed and installed grounding system helps to protect people and equipment from electrical shock and damage. Always consult with a qualified electrician or grounding engineer to ensure that your grounding system meets all applicable codes and standards. Here's an expanded explanation of the key components and considerations for metal building grounding systems, incorporating best practices and relevant code references. The primary purpose of a grounding system is to provide a low impedance path for fault currents to return to the source, allowing overcurrent protective devices like circuit breakers or fuses to quickly trip and clear the fault. This minimizes the risk of electrical shock and equipment damage. The grounding electrode system is the foundation of the grounding system. The National Electrical Code, or NEC, specifies several acceptable grounding electrodes, including metal and groundwater pipes. The metal water pipe must be in direct contact with the earth for at least 10 feet to qualify as a grounding electrode. It is also required to be electrically continuous. Concrete encased electrodes, often called U for grounds, consist of at least 20 feet of bare copper conductor, no smaller than number 4 American wire gauge, encased in concrete. This electrode is typically located near the bottom of a foundation or footing that is in direct contact with the earth. Ground rings are continuous conductors, typically bare copper, that encircle a building or structure and are buried directly in the earth at a depth of at least 30 inches. Rod and pipe electrodes must be at least 8 feet long and driven into the earth to a minimum depth of 8 feet. The NEC specifies the minimum size and type of rod or pipe electrode that can be used. The grounding electrode conductor, or GEC, connects the grounding electrode system to the building's main electrical panel or service equipment. The size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. The GEC must be securely connected to the grounding electrode and the service equipment using approved connectors and methods. Bonding is the process of connecting all metal parts of a building's electrical system together to create a low impedance path for fault currents. This includes metal conduit, metal enclosures, metal equipment frames, and any other metal parts that could become energized during a fault. Bonding is essential for minimizing voltage differences between different metal parts of the electrical system and reducing the risk of electrical shock. The NEC specifies the requirements for bonding in Article 250 Parts 5 and 6. Grounding electrode system installation considerations. Firstly, ensure that all grounding electrodes are installed in direct contact with the earth. Remove any paint, coatings, or other materials that could interfere with the electrical connection. Secondly, protect grounding electrode conductors from physical damage by routing them in conduit or other protective enclosures. Thirdly, use approved connectors and methods for connecting grounding electrode conductors to grounding electrodes and service equipment. Fourthly, inspect and test the grounding system regularly to ensure that it is functioning properly. Perform ground resistance testing to verify that the grounding system provides a low impedance path to ground. In addition to the requirements outlined in the NEC, there are several best practices for metal building grounding systems. Firstly, use multiple grounding electrodes to improve the effectiveness of the grounding system. Secondly, install a ground ring around the perimeter of the building to provide a low impedance ground path. Thirdly, bond all metal parts of the building's electrical system together to minimize voltage differences and reduce the risk of electrical shock. Fourthly, use surge protective devices, or SPDs, to protect sensitive electronic equipment from voltage surges caused by lightning or other electrical disturbances. Fifthly, consult with a qualified electrician or grounding engineer to design and install a grounding system that meets the specific needs of the building. The NEC requires that metal building frames be grounded to a grounding electrode system. This is typically accomplished by connecting the building frame to a ground ring or other grounding electrode using a grounding electrode conductor. The NEC also requires that metal building frames be bonded to the building's electrical system. This is typically accomplished by connecting the building frame to the equipment grounding conductor system. A counter-poise grounding system is a network of interconnected conductors that are buried in the earth around the perimeter of the building. The counter-poise helps to reduce the impedance of the grounding system, which improves its ability to conduct fault currents. The length and spacing of the counter-poise conductors are determined by the size and shape of the building, as well as the soil resistivity. Soil resistivity testing is an important part of designing a grounding system. Soil resistivity is a measure of how well the soil conducts electricity. The lower the soil resistivity, the better the soil conducts electricity and the more effective the grounding system will be. Soil resistivity testing can be performed using a variety of methods, including the Wenner 4-point method. The results of the soil resistivity testing should be used to determine the appropriate size and spacing of the grounding electrodes and counterpoise conductors. Regular inspection and testing of the grounding system are essential to ensure that it is functioning properly. The grounding system should be inspected visually for any signs of damage or corrosion. Ground resistance testing should be performed to verify that the grounding system provides a low impedance path to ground. The results of the inspection and testing should be documented and kept on file. Metal buildings are often used for a variety of purposes, including warehouses, factories, and office buildings. The electrical systems in metal buildings can be complex, and it is important to ensure that the grounding system is properly designed and installed. A properly designed and installed grounding system will help to protect people and equipment from electrical shock and damage. Always consult with a qualified electrician or grounding engineer to design and install a grounding system that meets the specific needs of the building. Understanding soil composition is crucial for effective grounding. Different soil types exhibit varying levels of resistivity, which directly impacts the efficiency of electrical current dissipation. Clay soils, characterized by fine particles and high moisture retention, generally offer a lower resistivity compared to sandy soils. Sandy soils, with their larger particles and poor water retention, tend to exhibit higher resistivity. Loam soils, a mixture of sand, silt, and clay, offer a moderate level of resistivity. Soil moisture content significantly affects resistivity. High moisture content generally lowers resistivity, enhancing the soil's ability to conduct electricity. Conversely, dry soils exhibit higher resistivity, impeding current flow. Soil temperature also plays a role. As temperature increases, resistivity tends to decrease due to enhanced ion mobility. Chemical composition, including the presence of salts and minerals, influences resistivity. Dissolved salts increase conductivity and lower resistivity, while the absence of such compounds can raise resistivity. Seasonal variations in moisture and temperature impact soil resistivity. During wet seasons, increased moisture levels lower resistivity, while dry seasons can lead to higher resistivity. When designing a grounding system, consider seasonal fluctuations and their effect on soil conductivity. Mitigation techniques for high soil resistivity include soil amendments. Adding materials like bentonite clay can improve moisture retention and lower resistivity. Groundwater can be used to increase moisture content and enhance conductivity. Chemical treatments, such as applying salt solutions, can temporarily lower resistivity. However, this approach requires careful consideration due to potential environmental impacts. Ground enhancement materials, or GEMS, are specifically designed to improve soil conductivity and grounding system performance. Proper compaction of soil around grounding electrodes and conductors ensures good contact and reduces resistance. The depth at which grounding electrodes and conductors are buried affects their performance. Deeper installations provide more stable moisture conditions and lower resistivity. Ground ring systems, encircling the building, provide a comprehensive grounding solution and improve overall system performance. The size, material, and configuration of grounding electrodes and conductors impact their effectiveness. Larger conductors and electrodes offer lower resistance and enhance current carrying capacity. Multiple grounding electrodes, spaced appropriately, can significantly improve grounding system performance. Proper spacing ensures that the electrodes do not interfere with each other and effectively dissipate fault currents. Regular testing and maintenance are essential for ensuring the long-term effectiveness of grounding systems. Visual inspections can identify any signs of damage or corrosion. Ground resistance testing verifies that the system meets required performance standards. Documentation of test results and maintenance activities is crucial for tracking system performance and identifying potential issues. Consulting with qualified professionals such as electrical engineers and grounding specialists ensures that grounding systems are designed and installed correctly. Professionals can assess site-specific conditions, perform soil resistivity testing, and recommend appropriate grounding solutions. Adhering to industry standards and best practices ensures that grounding systems meet safety requirements and provide reliable protection against electrical hazards. Understanding grounding principles, soil characteristics, and relevant codes and standards is essential for ensuring the safety and reliability of electrical systems in metal buildings. This information serves as a foundation for designing, installing, and maintaining effective grounding systems that protect people and equipment from electrical hazards.